This program will introduce the parts to the system and provide the step-by-step procedures for installing and removing it so that it can be a ready and familiar component in any situation. Hicks consists of three major sections. The cabin section, on both sides, is partly made up of the forward outboard roller assembly and rail. Center outboard roller assembly and rail, and aft outboard roller assembly and rail. These components utilize 26 5K tie-down fitting assemblies, 8 10K fitting assemblies, and 2 ring plug assemblies at station 360. 4 guide roller assemblies are secured in the center of the cabin section with 10 ring plug assemblies. The second section, the ramp section, includes a ramp outboard guide rail roller assembly on both the left and right sides, and a ramp inboard roller assembly on both the left and right sides. A separate ramp support assembly is also provided. The third section, the ramp extension section, uses 2 identical roller assemblies and 2 identical support assemblies. Before installing the system, carry out the following steps on both ramp extensions to modify them if they have not been modified. Place the master drill fixture over the ramp extension so that the alignment pins are snug against the ramp extension. Use at least 2 C-clamps to hold the fixture in position. Using the drill fixture guide holes, drill 6 starter holes. And then proceed to drill larger holes between .396 and .403 inches in diameter through both sides of the extensions. The drilled holes must be within tolerance, clean, and free of burrs to ensure the proper engagement of quick-release pins during installation. To prepare the aircraft for Hicks installation, clean out all dirt and debris. Remove the loading pole on the right-hand side of the aircraft if its retaining brackets are on the floor. Detach the ground cable and secure it to the airframe nearby. Remove the 3 loading pole retaining brackets at stations 327.680, 348.980, and 387.680. To begin cabin section installation procedures at station 240, 320, 400, and 481.780 on both sides of the aircraft, unscrew and remove the 8 10K rings from the fitting assemblies. For each of the 8 fitting assemblies, remove one of the 2 inboard inside screws holding the assembly and install an internal wrenching bolt and washer finger tight. Then remove the other 3 inside screws. If there is a protruding round head bolt beneath the aftmost 10K tie-down fitting, the bolt should be removed and discarded. Install a second internal wrenching bolt and washer, finger tight. It must also be inboard. Slide the 10K fitting assembly casting into position. Insert 2 outboard 12-point bolts and washers and tighten. After you have installed all 8 10K fitting assemblies, ensure that the 10K fitting assembly rings are laying parallel to the aircraft, and no 5K fitting assembly rings are facing outboard before rail installation. To begin installation of the rail and roller assemblies, angle each such that the rail bumper is clear of or just touching the buffer board. Rotate each rail to vertical. Some fore and aft movement may be necessary if interference occurs. If a floor patch causes interference problems, you will need to modify and repaint the interference area according to Hicks technical manual specifications. Using hex head bolts and washers, attach the rails to the 10K fitting assemblies. Make splice connections between the forward and center rails and the center and aft rails. Use 2 hex head bolts and washers per splice. At station 360, on the left and right sides, connect a ring plug assembly to the floor-mounted tie-down ring and the rail roller assembly. Ensure that the flat side of the conical washer is down. Connect the 26 5K tie-down fitting assemblies to the remaining 24 5K floor-mounted tie-down rings and to the rail roller assemblies. At station 356 on both sides, there will be no floor-mounted tie-down rings. To install the inboard roller guides, position the forward inboard guide roller assembly on butt line 0.000 so that the forward end is aligned at station 157. When installing all inboard roller guides, ensure that no 5K tie-down ring is blocked. Position the forward hatch inboard roller assembly on butt line 0.000 directly behind the forward guide roller assembly. Position the center inboard guide roller assembly directly behind the forward hatch inboard guide roller assembly. And position the aft inboard guide roller assembly directly behind the center inboard guide roller assembly. Connect tie-down assemblies to the 5K tie-down rings on the helicopter floor using centerline ring plug assemblies. To begin installation of hicks on the aircraft ramp, extend the ramp tongue. One person must then clean the screw heads, if required, of the 4 screws that attach the center skid pad and hold the screwdriver while resting on the ramp floor. At the same time, a second person must be under the ramp using a suitable wrench to remove the nuts securing the center skid pad. Remove the bottom center skid pad and attach the replacement ramp skid pad on the underside of the ramp. Use the previously removed hardware and BMS-5-44 sealant. Using the left and right-hand outboard guide rails as reference, mark the appropriate 12 bolts to be removed from the outboard left and right sides of the ramp floor. And remove the bolts. Remove the 3 bolts nearest the extended left and right transition rollers. Using the 2 ramp roller mounting bar assemblies and the 2 inboard roller assemblies, mark and then remove the appropriate 12 bolts from the left and right center area of the ramp floor. When finished, place the removed bolts in storage. To begin the actual installation of the ramp section, position the left and right-hand outboard guide rails on butt line 41.577 and butt line 42.432. Align the bolt holes with the outboard holes from which the bolts were removed, and attach the outboard guide rails to the helicopter ramp floor using 1 hex head bolt and 1 flat washer at the most forward bolt location on each guide rail. Secure each outboard guide rail at the remaining bolt locations using the remaining 11 hex head bolts and flat washers. Position the transition roller plates on the 3 holes located at or near butt line 32.024 on each side of the helicopter ramp, and secure the plates to the floor using 3 countersunk bolts each. Loose fit the bolts before tightening. Position 2 ramp roller mounting bar assemblies on butt line 17.587 over the center area holes from which bolts were removed. Secure the ramp roller mounting bar assemblies to the helicopter ramp floor using 4 hex head bolts and flat washers each. Position the ramp inboard roller assemblies over the center area holes from which the bolts were removed. Install 1 countersunk bolt at or near butt line 10.00 through the forward mounting plate for both inboard transition roller assemblies. Install 2 hex head bolts and flat washers at butt line 7.186 and butt line 6.057 through the forward mounting plate at each ramp inboard roller assembly. Install 2 hex head bolts and flat washers through the remaining holes in each forward mounting plate. Install 3 hex head bolts and flat washers to secure each aft mounting plate to the helicopter ramp floor. Attach each ramp inboard roller assembly to the mounting bar assemblies using 2 hex head bolts, flat washers, and self-locking nuts. Make certain that the flat washers are used under the component which turns, either the nut or bolt. To begin installation of hicks on the ramp extensions, position a ramp extension roller assembly on both the left and right ramp extensions so that the 6 quick-release pins on each assembly engage the holes drilled earlier. If required to use the ramp in the raised position for loading or unloading, adjust the support to the proper height and position the ramp support assembly so that the support pins engage both ramp support holes in the replacement ramp skid pad. If required to use the ramp extensions, position a ramp support assembly under each ramp extension so that the support pin is engaged. This completes the procedures for installing the hicks. Removal procedures, if required, are simply the reverse, except the 10K fitting assemblies and the ramp skid pad are left in place. Hopefully, the installation and removal of the helicopter internal cargo handling system will become an easy and well-known task. It certainly makes loading and unloading easier and faster, not to mention safer, in situations where speed is of the utmost importance.
The dependence upon electricity in aircraft has grown rapidly over the years. Present-day aircraft rely heavily upon electric appliances for the proper performance of their missions. In turn, these appliances depend upon an adequate source of electric power. For most electrically operated Army aircraft, this power is supplied by one of 3 direct current DC power sources: a battery, an external power unit, or a generator. This program will review these 3 power sources: management, distribution, and interrelationship within the OH-58AC series DC electrical system. Let's begin introducing power into the aircraft using the battery. For all practical purposes, the battery is considered the emergency power source and alternate starting source of power. Using a wiring diagram of the OH-58AC DC electrical system, let's follow the flow of power from the battery. Start at the battery and move along the positive wire to terminal A2 located on the battery relay. Continue following the jumper wire to terminal X1. This puts controlling power on the relay. All that is needed to activate the relay now is a ground. Find X2 on the battery relay and follow this wire to the battery switch. You can see an opened circuit exists at the battery switch. Close the switch. This completes the ground for the battery relay. With the ground completed, the plunger falls within the battery relay and allows the power that was waiting at terminal A2 to go across to terminal A1. This power is then directed to the battery bus, main DC bus, and overhead console essential bus for use. Another means of introducing power into the aircraft is with an external power unit connected to the aircraft's external power receptacle, located on the lower right side of the aircraft's avionics compartment. This particular source of power should be used for all ground starts and ground troubleshooting. Start at the negative prong on the external power receptacle. You can see this creates our common ground to the airframe. Find the center positive prong on the external power receptacle. Follow this wire to terminal A1 on the external power relay. This puts external power on the relay. Return to the external power receptacle. Find the small positive prong on the external power receptacle and trace that wire to X1 on the external power relay. This puts controlling power on the external power relay. Continue to follow this same wire from X1 to the generator fail relay. Follow this wire through the generator fail relay to the non-essential bus switch. With the switch in the normal position, continue the wire trace to X1 on the non-essential bus relay. This puts controlling power at the non-essential bus relay. At this point, the relay will close, so long as a good ground exists at X2 on the non-essential bus relay. There will be no transference of power to the non-essential bus, however, until external power has been introduced to the bus. Returning now to the external power relay, complete the ground at X2. With the ground completed, the plunger falls within the external power relay. The power that was waiting at terminal A1 goes across and is directed through A2 to the battery bus, main DC bus, overhead console, and non-essential bus for use. Non-essential bus operation is now possible. Remember, the plunger is down within the non-essential bus relay, allowing the arriving external power to flow from A2 to A1 en route to the non-essential bus. Since the non-essential bus operation is possible in either the normal or manual position, complete the wire trace for operations in the manual position. Return to the overhead console essential bus. Follow the wire leaving that bus through the generator and bus reset circuit breaker. Continue the trace to the non-essential bus switch. With the switch placed in the manual position, controlling power is placed on the non-essential bus relay at X1. The process of transferring power is then duplicated as with operations in the normal mode. This is why non-essential bus operation is possible either in the normal or manual position. Now that power is on board the aircraft, you need to start the engine. To do this, you would use the combination type starter generator, located on the underside of the engine to the right of the aircraft's center line. In addition to starting the engine, the starter generator is used to charge the battery and supply power to all DC electrical components. To start this cycle, begin at the overhead console essential bus and find the igniter circuit breaker. Follow that wire to the pilot's collective stick switch box. Without the starter switch depressed, power from the bus is now laying in wait at the switch. Now, depress the starter switch. Continue the trace through the starter switch. Notice the exciter has now been energized. The exciter in turn energizes the igniters and completes this circuit. Return to the overhead console essential bus and find the starter circuit breaker. Follow that wire through the starter circuit breaker to the pilot's collective stick switch box. Without the starter switch depressed, power from the bus is laying in wait at the switch. Now, depress the starter switch. Continue the trace through the switch. You will find this power is being directed to X1 on the starter relay. You have just placed controlling power on the starter relay. Complete the ground on the starter relay at X2. With the ground completed, the plunger falls, and the power on the bus is allowed to flow across the starter relay's terminal A2 through A1 and onto the starter generator's pin C. However, the arriving power will not start the aircraft. The voltage regulator must first change the generator into a motor. Return to the X1 terminal on the starter relay. While controlling power is being applied to the starter relay, power is also being sent to the voltage regulator's pin C. Upon receiving this power from the starter relay's X1, the voltage regulator does two things. One, increases the resistance in the shunt field windings within the generator. This action stops or severely reduces the output of electrons produced from armature rotation within the field of the generator. This signal is sent to the starter generator's pin D from the voltage regulator's pin G. 2. The starter generator's pin A also receives a signal from the voltage regulator's pin M. 1 volt is applied during the start process to allow the starter to return to a generator at the completion of the start process. At the completion of the start cycle, the generator immediately begins to produce electrons. Find pin B on the starter generator. Begin the wire trace to the generator shunt. Notice the wires going to the load meter. Since the generator switch is off, the unregulated voltage being produced from the generator is not being used. Therefore, the load meter will not register. Continue the wire trace to the line control relay's terminal A1. At this time, controlling power is not being applied to X1. Continue the trace through the generator field circuit breaker to the generator switch. Unregulated voltage now exists at the generator switch. Place the generator switch to the on position. The generator switch is a single-throw, double-pole switch. Looking at the switch, the flipper on the left will displace to the on position. At the same time, the flipper on the right will follow. This action will allow the awaiting unregulated voltage to move through the generator switch to pin J at the voltage regulator. For the first time, the voltage regulator has an opportunity to sample the voltage being produced by the generator. The voltage regulator, in its operation, varies the resistance within the shunt field windings through the voltage regulator's pin G to the generator's pin D. This increasing and decreasing of generator shunt field windings by the voltage regulator regulates the output of the generator. With this most important task completed, the voltage regulator will allow controlling power to leave the regulator via pin H and be transmitted to the line control relay's X1. Before completing the ground X2 and allowing the relay to close, complete the wire trace from the line control relay's X1. Follow that wire to the generator fail relay. In completing this trace, you can easily see this will place controlling power on the generator fail relay's X1. With the ground X2 completed, you can see the plunger within the relay will retract and both flippers will displace. The displacement of the lower flipper will create an open circuit to pin L. Pin L represents the generator caution light on the master caution panel. The upper flipper's displacement will allow for non-essential bus operations with the non-essential bus switch in either the normal or manual position. Return to the line control relay and complete the ground X2. With the ground completed, the plunger will fall, and the now regulated voltage will be transmitted across terminals A1 to A2 within the line control relay. This power is sent to the main DC bus, the overhead essential bus, and to the battery bus. From the battery bus, with the battery switch on, you can easily see how the power is allowed to cross the A terminals within the battery relay and onto the battery for recharging. This is system's normal operations. The generator voltage output must exceed the battery voltage output by 0.30 to 0.42 volts before any of the preceding can happen. The question must then be asked, what happens if the voltage output of the generator is weaker than the battery voltage? This is most often the case when the voltage regulator is incorrectly adjusted or malfunctioning. Let's look at the case of a poorly adjusted voltage regulator. Return to the line control relay. Remember, the voltage regulator applies controlling power to X1 on the line control relay. With the ground completed at X2, the relay closes, and the power waiting at A1 attempts to cross over to the bus. This is an attempt at system's normal operation. With systems abnormal, the generator weaker than the bus by 0.30 to 0.42 volts, battery power is allowed to cross the line control relay's terminals A2 to A1. Follow the trace through the generator field circuit breaker to the generator switch. Remember, the generator switch is on. So that same power continues through the generator switch to the voltage regulator pin J. The under voltage condition is sensed by the voltage regulator, and it attempts to compensate by regulating the resistance in the generator's shunt field windings using the voltage regulator's pin G to the generator's pin D. If the voltage regulator is unable to regulate the generator output, the voltage regulator will terminate the signal from the voltage regulator's pin H to X1 on the line control relay. The plunger will pop up and no longer allow the battery power to cross the A terminals on the line control relay. There is a built-in option that will allow you to reclaim the generator. This reclaiming is called flashing the field. When the generator comes offline, battery power will still exist on the bus. To begin the field flashing trace, find the overhead console essential bus. On this bus, find the generator and bus reset circuit breaker. Go through this breaker to the generator switch. Move the switch to the reset position. This will displace both the flippers within the switch to its opposite most position. This action will allow the waiting battery power at the generator switch to travel through the generator switch to the voltage regulator's pin D. At this time, that same power is sent through the voltage regulator, leaving the voltage regulator at pin M and arriving at the generator via pin A. It only takes a moment to flash the field. At the completion of this procedure, return the generator switch to the on position. This will allow the generating cycle to be repeated again as previously explained. Having been electrically charged with information on the three sources of DC power, their management, and flow within the OH58AC series DC electrical system, you should now better be able to supervise and orchestrate, thus alleviating black box troubleshooting, saving an immeasurable waste of maintenance, man-hours, and materials.
This is the new ship you'll be working with, the AH-1G Huey Cobra attack helicopter. It is the first helicopter in aviation history to be designed as a weapons platform. It is very fast, can carry more than 1 ton of ordnance, and represents a significant increase in fire support for the Army's combat forces. The whole design was based on using many of the dynamic components of the UH-1 series helicopter and wrapping a new, clean, aerodynamic shape around them. It is this new fuselage which we should look at first, for it is a different breed of cat from the previous UH-1 models. On the earlier Hueys, all of the access panels and doors were made of thin aluminum skin. For all practical purposes, they did nothing more than cover the airframe structure. They could all be removed or opened at once, and the aircraft could be moved in this condition. The AH-1G is much more like a jet fighter. Many of the airframe panels are part of the structural integrity of the aircraft. They have aluminum or titanium faces with fiberglass honeycomb backs. They are designed to carry airframe loads and do it effectively. Let's look at the most extreme case. With the aft fuel tank access panel removed, the aircraft is in a marginal structural condition. Should someone try to move the ship by the tail, structural damage might occur. Obviously, to carry the loads which the structural panel does, a support such as a jack should be used under the tail section. As you go around the ship, you will find these structural panels everywhere. It may help you to understand why you have to remove 40 screws sometimes when you know that the panel could be held on with 6. Although the panel could be secured with so few, the aerodynamic flight loads couldn't be carried without using all 40. You'll also notice the screws themselves, flush Phillips head screws. They have been used because of the aerodynamic integrity of the AH-1G. They require a Phillips head screwdriver in most cases. The Army knows that there will be a lot of these to remove and replace, so there have been additional screwdrivers of the right size and type added to your tools for this ship. Components which produce unnecessary drag on the Huey Cobra have been eliminated. This design philosophy is apparent throughout the whole ship. Everything has been faired in or covered over. Take those rocket pods, for example. The shaped nose covers can make a difference of 11 knots in aircraft speed. But let's start walking around the ship and see where the main components which interest the airframe mechanic are located. The nose compartment door consists of a contoured laminated fiberglass panel with spring-loaded hinges and spring latch fasteners. A door on each side of the fuselage, immediately after the TAT-102 gun turret, gives access to the ammunition compartment. The cockpit canopy is 1/4 inch stretched acrylic plastic covering the entire cockpit area. The pilot's and gunner's door latches are flush mounted and located in the lower edges of each of the doors, which hinge upward and are held open by 3-position variable struts. When the jettison handles, located in the top of the canopy, are turned, the doors are separated from the canopy. 2 doors, one on each side of the fuselage, directly aft of the cockpit canopy, provide access to the hydraulic reservoirs. Construction is laminated fiberglass and honeycomb core. The engine and transmission are cowled on each side by doors which swing open fore and aft on articulated hinges. The pylon area is covered by a laminated fiberglass enclosure. Doors are provided in the center section for access to the swash plate and in the aft section for access to the engine oil tank. A 1-piece enclosure streamlines the engine tailpipe. 290 pounds of advanced type armor materials have been integrated within the airframe structure to protect the crew and vital aircraft components. Crew seats are constructed of dual hardness steel with under and side panels of boron carbide. Engine, compressor section, and fuel control are protected by boron carbide panels. The pilot seat is a vertically adjustable 1-piece bucket-type assembly mounted on 2 vertical tubes which hold it in place on the airframe structure. The gunner seat is a 2-piece bucket-type assembly consisting of a back and bottom. The 2 parts are joined together and held in a fixed position when bolted in place directly to the airframe structure and is not adjustable. The tail boom is an aluminum alloy structure covered by aluminum skin. As in previous versions of the UH-1, a synchronized elevator is located on the tail boom. Doors and panels are provided at various locations on the tail boom to allow interior access for inspection and maintenance. The tail rotor shaft is enclosed by sheet metal covers on the tail boom and on the leading edge of the fin. They hinge open to the right. and secure in the closed position with twist fasteners. The tail rotor drive shafts are the same as other Huey helicopters. The 42 and 90-degree gearboxes are also identical to the UH-1 series of aircraft. The tail rotor assembly is similar to the UH-1C, except for a design change in the shimming method for establishing trunnion centering. A completely new tail rotor hub is currently under evaluation and will probably be installed on later production AH-1Gs. Stub wings mounted on the fuselage are provided primarily as a mounting accommodation for external weapon stores. Each wing is attached to fuselage fittings with 5 bolts and has removable leading edge sections. The alighting gear consists of 2 skid tubes and 2 arched cross tubes of formed aluminum alloy. Fittings are provided on the skid tubes to accommodate ground handling wheels. To prevent abrasion and damage from contact with the ground, replaceable steel skid shoes cover the bottom side of the skid tubes. The AH-1G main rotor is 44 feet in diameter and has 2 27-inch cord blades on a 540 door hinge type hub. This system enables the Cobra to fly at high air speeds with exceptionally low vibration levels. The main rotor assembly is the same as the UH-1C. The pitch horns are different due to the fact that the stabilizer bar of the C model has been replaced by the SAS system. The mast is also not interchangeable, since it is heavier and has a series of different splines. Now that we have been around the ship, you will have noticed that a lot of components look similar to the UH-1 series of Hueys. While a lot of components look similar, but are stronger. The whole airframe structure is substantially beefed up, and individual items, such as a landing skid, are completely different. It is stronger and attaches entirely differently than UH-1 skids. The rotor blades are the principal source of lift for the helicopter. They are made from aluminum honeycomb and are bolted to the grips at the inboard end. The blades require careful inspection for nicks, scratches, dents, and voids. Your TM55-1520-221-20 has very specific descriptions as to what should be fixed and how to do it, and what should not be repaired but replaced. Like many other areas of the aircraft, this will be one of the most important parts of your job. Knowing the difference between what you can and should repair and what you should replace. Of course, all blades must be tracked after every installation. And this is a good time to go back to the Dash 20 and see the new type of troubleshooting table which has been provided. In clear, step-by-step procedures, the entire tracking operation is detailed. And after each step, there are choices to be made, depending upon how the test worked. The swash plate and support assembly is similar to the UH-1C, except the components are stronger. The swash plate uniball friction device and the collective sleeve collet are also similar to the UH-1C. The transmission is located directly ahead of the engine and is suspended by pylon isolating mounts on structural supports extending above the power plant deck. The unit is coupled to the engine through a short drive shaft. The transmission provides drive angle change and speed reduction through a train of spiral bevel gears and 2-stage planetary gears to drive the main rotor mast. A freewheel clutch in the input quill coupling disengages to allow main rotor and gear train to turn freely when engine is stopped or is idling below rotor driving speed, such as in autorotational descent. The AH-1G uses the Huey Universal Transmission. It is the same basic transmission as used on the UH-1 helicopters, except that the AH-1G has no main generator. The starter generator is used as the main generator. A separate film in this series on the AH-1G covers the Huey Universal Transmission. It details where the quills, which are particular to individual aircraft, are located and how these should be installed to adapt the basic universal transmission to any Huey helicopter. The complete engine and power transfer system is enclosed in an easily opened or quickly removable lightweight cowling. The turbine engine and its accessories are located after the transmission and are mounted on a platform deck to provide maximum accessibility for servicing and maintenance. The T-53L13 series gas turbine engine is a free turbine type, flat rated at 1100 shaft horsepower. Flat rating refers to the limitation on the engine due to the airframe. The engine itself is capable of 1400 shaft horsepower. The engine consists of the usual 5 sections: inlet, compressor, diffuser, combustor, and exhaust sections. The bipod and tripod engine mounts on the AH-1G are the same as on previous Huey helicopters. The tailpipe is surrounded by an ejector shroud that extends several inches past the end of the tailpipe. This ejector mixes cool air with the exhaust gases to reduce the infrared radiation. The open end of the tailpipe is directly above the tail boom and directed slightly upward so that a view of the hot end of the turbine is possible only from a position that is above and behind the helicopter. 2 similar but separate hydraulic systems are used to operate flight control power cylinders, stability augmentation system servo actuators, and the armament turret. Systems number 1 and number 2 are exactly alike as to their reservoirs, transmission-driven pumps, and module assemblies. If one system is disabled, the other system can still operate normally. In addition to operations for both systems, hydraulic system number 1 has the following special functions: tail rotor controls hydraulic cylinder, yaw stability augmentation system servo actuator, emergency collective hydraulic power provisions, and cyclic controls accumulator and lockout valve. Hydraulic system number 2 has the following special functions: armament system hydraulic power provisions, and pitch and roll stability augmentation system servo actuators. The electrical power systems consist of a DC and an AC system. The 28-volt direct current supply system is a single conductor system with the negative lead grounded to the helicopter structure. Alternating current is supplied by one 100-volt ampere single-phase inverter that converts the 28-volt DC to 115 volts AC to the SAS system, fuel quantity, gyro compass, attitude indicator, AC fail relay, and 26-volt transformer. The 26-volt AC transformer, in turn, supplies AC to the following: fuel pressure, engine oil pressure, transmission oil pressure, torque pressure, and heading indicator. The primary flight control systems are the main rotor collective, fore and aft cyclic and lateral cyclic, and the tail rotor controls. Each of these is a system of mechanical linkage assisted by hydraulic servo cylinders connecting the pilot's and gunner's control sticks and pedals to those mechanisms which rotate with and directly control the main rotor and tail rotor. Obviously, the tandem seating configuration of the Huey Cobra will pose some complications in control rigging, since the system must be more complex than the side-by-side seating of earlier UH-1 aircraft. The AH-1G stability augmentation system is a 3-axis stability and control augmentation system integrated into the conventional helicopter fore and aft, lateral, and directional flight controls. SAS provides a highly damped airframe during wind gusts and weapons recoil and was designed primarily to provide a stable weapons platform. One of the systems on the AH-1G, which is completely different from previous Huey models, is heating and ventilating. The crew compartments are ventilated by air drawn through a screen on the front of the pylon fairing and forced through the distribution system by a continuously operated transmission-driven blower. Air is distributed through adjustable ventilators on both instrument panels, vents to sides of canopy, and cushions of crew seats. Air leaves the compartments through a blower opening located in the aft bulkhead. Heat is provided by bleed air from the engine compressor system. Bleed air is also used through windshield nozzles for rain removal. Rain removal from the windshield is accomplished by setting the selector switch on the instrument panel to rain removal position. When the selector switch is in the rain removal position, no bleed air flows into the crew compartment. Armament is the Huey Cobra's reason for existence, and it has a great variety. Let's start at the chin turret. The TAT-102 armament subsystem is a hydraulically and electrically operated system providing wide angular coverage and rapid fire. The weapon is a 7.62 millimeter hydraulically powered automatic multi-barrel minigun. The weapon incorporates 6 barrels and 6 bolt assemblies which revolve about the longitudinal axis of the weapon. The weapon with the delinking feeder is mounted in the turret and is capable of short bursts or prolonged firing at rates of either 1,300 or 4,000 rounds per minute. The gunner's fire control panel is located in the co-pilot gunner station in the right deck, forward of the flight controls. The sighting station consists essentially of a simple compensating sight head and hand grip assembly attached to the aircraft floor by means of a 5 degrees of freedom support structure. The ammunition feed system consists basically of ammunition box assemblies, a crossover feed assembly, a flexible ammunition chute, and a synchronized cartridge drive assembly. The ammunition box assemblies are mounted in the aircraft aft of the turret assembly. The external stores pylon installed on the AH-1G equips the helicopters for carrying various external stores or weapons. The ejector rack of the pylon is equipped with an electrically operated ballistic emergency jettison device in each inboard and outboard ejector rack. The ejector racks must be cleaned at the end of each firing day in which the emergency jettison is used. The orifice in the outboard ejector rack must be replaced after each second jettison of stores. Installed in the AH-1G is the XM-20 smoke grenade dispenser, which releases standard smoke grenades used for spotting and identification. This dispenser is loaded with M8 or M18 smoke hand grenades by the armament crew prior to flight. It consists of 2 clusters of 6 canisters, either of which may be selected by the pilot. The wings each have 2 hardpoints for ordnance stores. Armament currently qualified for use includes the XM-157 launcher, which fires 7 2.75-inch folding fin aerial rockets. Also, the larger XM-159 launcher, which can fire 19 rockets of the same type. Both types of launchers are reusable. Inboard hardpoints on each wing can accommodate the XM-18 minigun pod. The gun fires 7.62 millimeter ammunition. Both the gun and the feed system are powered by a self-contained electrical system. The mix of weapons will change depending upon mission requirements, since the variety of armament available provides an extremely versatile attack capability. Your TM-20 contains complete requirements for special inspection, test flight inspection, overhaul and retirement, and the standards of serviceability for the AH-1G. There is flexibility in performance of these inspections to allow for the variety of climate and terrain in which the Huey Cobra will serve. The Army TMs, your -20 and -35 handbooks, use them And be sure to add the periodic revisions to the books. Don't forget, the pilots of your unit depend on your skill and dedication. The AH-1G and the UH-1C don't have identical rotors. Even casual observation will verify that fact. But they are interchangeable. On the Huey-C model, there is a stabilizer bar which is plainly visible. And there is none on the Huey-Cobra. And that is the single difference between the two systems, the method of stabilization. Let's look first at the UH-1C and how the stabilizer bar works. The open end of the pitch horns faces upward on the UH-1C, and the pitch change tube is attached to the stabilizer bar. This bar has weights which are rotated about the axis of the rotor, thus creating mechanical forces which can be used for stabilization. So the UH-1C has a mechanical system of stabilization. The AH-1G has no stabilizer bar because it has an electronic stability augmentation system. The mechanical components have been replaced by the SAS system, which feeds directly into the control system the input required to produce airframe damping. Since the Huey-Cobra was designed specifically as an attack helicopter, every effort was made to make the ship as immune as possible to changes in attitude produced by wind gusts or weapon recoil. Since the pitch horn and mast are the only parts which are different, the two rotor systems are interchangeable. And DS and GS maintenance is now permitted to change pitch horns in order to convert components of one rotor system to another. The biggest aspect of maintenance on the rotor system is the inspection of the blades. There are two primary types of damage to look for: nicks, scratches, dents, holes, and voids. A void is defined as any unbonded area which is supposed to be bonded. Like other areas of the aircraft, in blade inspection, one of the most important parts of your job will be in knowing what blades you can repair and what blades you should replace. Extremely detailed instructions are contained in your TM 221-20. This book, kept up to date by including the periodic revisions, is your Bible for maintaining the rotor system. The entire blade assembly is usually removed if blade replacement is indicated, or when making the required 200 or 600-hour inspection of the rotor hub as detailed in your -20. The main rotor hub should be supported on a stand, and each blade supported so that the leading edge is straight. First, detach the drag brace from the blade by removing the nut, washer, bolt, and shims. Save the shims for use in reassembly. Do not change the adjustment on the drag brace. Remove the locking screw from the nut which holds the blade retaining bolt. You have a wrench which fits this nut. With nut and washers removed, the blade retaining bolt can now be removed. Should binding occur, merely raise and lower the tip of the rotor blade slowly. By keeping pressure on the bolt, a point will be found where the bolt withdraws easily. The blade retaining bolt is color-coded for reinstallation in the same location. One important maintenance assembly is the main rotor hub. The 200 or 600-hour inspection detailed in your -20 will require this effort. Since the smoothness of rotor action will depend to a large extent on how carefully the adjustments in this area are made, care should be taken to follow handbook instructions. Some of you who are familiar with the earlier models of the 540 rotor system on the UH-1C may observe another detail which is present on the AH-1G rotor system. It is the sand deflector which has been added to all 540 rotor systems. It was found that when the UH-1C was operated in sandy environments, the shovel action of the main rotor grips would collect sand in the grip area against the outboard grip bearing seal. Improper seal gap or seal deterioration would allow sand to bypass the seal and enter the Teflon bearing area. The addition of the sand deflector coupled with the new seal and radius ring has been an effective cure. The inspection time for this unit has increased from 200 to 600 hours. To disassemble the hub, the pitch horn may be detached by removal of 3 retaining bolts. It helps on reassembly if the top surface of the inboard bearing housing is indexed with a small spot of quick-drying paint. Remove housing bolts from inboard end of grip. Index the grip retaining nut to grip. Remove lock nut and clamp. Then remove the nut, counting the number of turns required. If grip spacing tool is not available, record the number of turns for reference at time of reassembly. Remove the grip, using care not to damage the threads of the outboard strap fitting. Loosen 2 nuts on the extension bolts. Remove the leading edge side bolt and swing grip and extension forward on the trailing edge bolt. Remove the housing from the inboard end of the grip. Inspection of the Teflon bearings should now follow. It is important to learn what is acceptable bearing wear and what wear requires bearing replacement. There are 6 photos in your Dash 35 which show various types of bearing wear with both acceptable and unacceptable wear patterns. Study them carefully and use them as standards for comparison with bearings you remove on the flight line. The whole subject of inspection of rotor components requires a degree of detail which we can't go into in this film. There is specific, detailed information on each item in the Dash 35. Perspective drawings indicate what tolerances are allowed on the various mating surfaces. Also, damage limits on main rotor hub and blade grips. Again, following the steps outlined in the handbook will get you through the whole procedure, and you will end up with a smooth running rotor system. One small but important detail during reassembly is the adjustment of outboard grip bearing seals. AH-1G main rotor heads incorporate a new type radius ring employing a bonded plastic shield. When adjusting this shielded ring, the gap should be set from 0 thousandths to 40 thousandths. If replacement of the ring with shielded type is not possible, the older unshielded ring may be used. Gap for the unshielded ring should be set at 30 thousandths, with the tolerance being from 30 thousandths to 70 thousandths. When the older unshielded ring is used, the inspection interval is also reduced to 200 hours. Since all the rotating components of the rotor system are subjected to constant vibration, the tightness of the bolts which hold the components in place is of extreme importance. There are 27 fastening points and 14 different torque values. You may remember some of them, but it's doubtful that you will learn them all. The best bet is to refer to the figure in Chapter 1 of the Dash 20. All the values and locations are clearly indicated. Many men make a copy and keep it handy for reference on the flight line. Of course, all blades must be tracked after every installation. And this is a good point to go back to the Dash 20 and see the new type of troubleshooting table which has been provided. In clear step-by-step procedures, the entire tracking operation is detailed. And after each step, there are choices to be made depending upon how the test worked. It has been proven in actual demonstrations that even an untrained mechanic can successfully track the blades of a Huey Cobra just by following the steps outlined in this troubleshooting table. The AH-1G has pioneered in the use of tables such as this, and you will begin to see them appear in Army handbooks on other UH-1 aircraft. Of course, to paraphrase the old song, it takes two to track, the mechanic and the pilot, since the final determination of what vibration may be present has to be made in the air. And your unit's test pilot has been specially trained to work with maintenance personnel in detecting and eliminating rotor and pylon vibration. This additional pilot training is indicative of the increasing emphasis the Army places on maintenance. The problem of keeping aircraft flying is the concern of everyone. As aircraft become more sophisticated, your job becomes more demanding and also more important. The AH-1G helicopter includes the most advanced armament systems, ranging from large caliber guns to rockets. Yet no matter how accurate these weapons might be, their systems accuracy is dependent upon aircraft stability. The error cone for a weapon is influenced by aircraft movements around three axes: pitch, roll, and yaw. Errors in fire direction can be induced through weapon recoil moving the airframe, aerodynamic gusts pushing the aircraft or rotor system, and other mechanisms being established from the flight environment. Therefore, accurate fire coverage is dependent upon the basic stability of the airframe under all flight conditions, hover and forward modes, leading to the axiom of design that stability yields accuracy. During the design of the AH-1G, this axiom was applied. The experience gained with the UH-1C and UH-1D pointed to the two major design requirements. First, the stability system must provide immediate damping of the airframe from external disturbances, and this must be done so that wide-angle weapons coverage and rapid-fire capability were not impaired. Second, the system must work with the pilot at all times to assure him of positive, high-quality flight control response. Two means of providing stability to helicopters are available: mechanical systems and electromechanical systems. On the UH-1 helicopters, stability is achieved by the use of a stabilizer bar assembly attached to the main rotor. As the rotor system turns, the stabilizer bar turns with it. And since the bar is a carefully balanced dynamic system, it develops inertia and gyroscopic forces. These stabilizing forces are induced into the main rotor. The pilot's control forces are also fed through the stabilizer bar into the rotor blades. Because both types of inputs, pilot and inertial, are feeding together, a compromise between pilot control and stabilization occurs. This technique is adequate for a troop transport, but is entirely inadequate for use on the AH-1G. Control response for airframe damping and pilot handling cannot be solved utilizing a mechanical system. Electromechanical systems, as opposed to mechanical stability systems, use an electrical network in conjunction with mechanical devices. A sensing device, such as a rate gyro, is used to provide electrical signals into the network. The network then converts them into commands for the mechanical input into the flight control system. This is done in addition to and concurrent with the inputs made by the pilot. There are two categories of electromechanical stability systems. Single loop, usually called ASE or automatic stabilization equipment, and multi-loop type, often called SAS, for stability augmentation system. Neither one of these is an autopilot system. An autopilot has a completely different function. Dismiss this term entirely. A multi-loop stability augmentation system is used on the AH-1G. It provides for airframe damping and also allows the pilot to override the system commands if he desires. Airframe damping occurs in a similar manner to a single-loop system, but the override feature utilizes an extra electrical signal network. The SAS system is integrated with the conventional helicopter flight controls to provide three-axis stabilization and control of the aircraft. Three basic loops are used in the system: the rate gyros, the control motion transducers, and the actuator feedback transducers. In order to better understand the components of the SAS, it is important to understand what a transducer is. The role of a transducer is to convert one form of energy into another. For instance, a photocell is a transducer. It converts the electromagnetic energy incident upon its sensitive face in the form of light waves into an electrical current. Likewise, a potentiometer is a transducer. It can convert mechanical energy measured in the form of a change in length, such as the movement of a piston, into electrical energy, or as a change in voltage through its circuitry. Transducers allow mechanical motion to be interpreted electrically. The SAS is a three-axis stability augmentation system. Therefore, it is integrated into the cyclic and directional aircraft flight control systems. The first is the fore and aft cyclic control for aircraft pitch changes. The second is the lateral cyclic control for control in roll. And third, the directional control system for changes about the yaw axis. Pilot inputs through the cyclic stick and rudder pedals, whether in pitch, roll, or yaw, all feed through the SAS system. It is important to realize that when the SAS is turned off, the flight controls operate in the conventional manner. With the SAS in operation, an additional mechanical input to the pitch, roll, and yaw flight controls is added to each. Let's move on to the SAS trainer, where the functioning of the individual components can be better understood, since there are no other elements to distract us. Three electrical signals are used in the SAS system. The first comes from the control motion transducers, located in three separate spots within the aircraft push-pull mechanical flight control system. These transducers are linear potentiometers which convert movement of the control rods through a bell crank into a forward feed loop input signal to the compensating circuit. This signal feeds into the sensor amplifier unit, where it is summoned, shaped, and mixed electronically with the rate gyro signal. Mixing occurs in the compensating network. The second signal from the rate gyro occurs when the aircraft pitches, rolls, or yaws, whether pilot-induced or caused by other forces acting on the airframe. If the pilot is not inducing changes and aircraft movement occurs, the rate gyro sends a signal to the compensating network. It is then passed onto the valve driver amplifier module, causing the actuator servo to extend or retract the actuator to correct for the deviation. The third signal comes from the actuator feedback transducer. This component is a linear variable differential transformer mounted internally in the actuator. It provides position information on the actuator when the actuator extends or retracts to return the actuator to the neutral position. All three of these signals, rate gyro, control motion transducer output, and feedback transducer output are fed into the sensor amplifier compensating network, where they are processed and provided as a correction signal to the valve driver amplifier and the servo valve. The compensating network is actually a printed circuit board with all of its integrated components in a central location. The valve driver amplifier is an encapsulated module located on each circuit board. This component provides the signal to the servo valve on each actuator. The servo valve is an integral part of the actuator. Through it, the electrical signal from the SAS loop can become a mechanical force to operate the flight control linkage. The electrical signal from the valve driver amplifier commands the servo valve to post hydraulic fluid so that the actuator linkage is extended or retracted, thereby inducing a change in the aerodynamic surfaces of the helicopter. Electro-hydraulic actuators are installed in each one of the control systems for pitch, roll, and yaw. They have control tubes and clevis attachments for installation in the control system. These actuators are interchangeable. The actuator authority is limited to control movement of 12.5% either side of normal position. And should the hydraulic or electrical system fail, the actuator is designed to automatically center and lock, thereby becoming a rigid mechanical link in the system. This allows the pilot to fly using normal mechanical control. Circuit protection for the SAS is handled through a 5-amp DC breaker located on the aircraft 28-volt DC circuit breaker panel. A 1-amp fuse for 28 volts is located in the sensor amplifier unit, as well as a spare fuse and holder. The third protective unit is a 1-amp AC breaker located on the 115-volt AC circuit breaker panel. The control panel is located only in the pilot's cockpit. This panel controls all the functions of SAS except for emergency disconnect. It contains a 2-position switch which turns power off and on to the DC and AC circuits, and 3 channel engage switches: pitch, roll, and yaw. Closure of each of these switches provides 28 volts DC power to the hydraulic solenoid valves. 3 no-go indicator lights, 1 for each axis, indicate an out-of-tolerance condition or an unexpired warm-up time in the SAS system. The stability augmentation system is dependent on the use of hydraulic components to convert the electrical sensing commands into control link forces. Therefore, it is a vital subsystem. The main hydraulic system for the aircraft is used as a supply for the SAS. The filters used are 10-micron particle pressure inline type. They are replaceable as complete assemblies and are interchangeable in location. When installing each filter, ensure that the arrow labeled on the side of the filter points toward the solenoid valve. Hydraulic pressure is taken from 2 systems for use by the SAS. System number 1 is used to power the actuator for directional control, and system number 2 is used to power the fore and aft and lateral cyclic actuators. The neutral condition in the actuator occurs when the engine is operating. The electrical power is on, and the SAS axis engage switches are on. Hydraulic pressure is supplied to the actuator. In the neutral position, the servo valve does not supply fluid to the piston. Fluid is allowed to flow through an orifice to act upon the spring-loaded locks. Compression of the locks occurs fully at 300 psi. The piston is now free to be moved in either direction. Note that no fluid is acting on the piston at this time. Therefore, the term neutral applies. The actuator retracts when the servo valve moves to allow the fluid to flow into the right-hand piston area and force the piston to the left. Fluid contained in the left piston area flows out the return line. For actuator extension, the reverse process occurs. The servo valve ports the fluid to the left piston area, applying force to the piston face, causing it to move to the right. Note that in both cases of movement, fluid was provided to the lock chambers to keep them released, not interfering with piston travel. SAS is so sensitive that it is impossible for a man to hold the sensor unit steadily enough, even with his hand supported, that signals are not fed into the rotor system. Even the slight pulsations which aren't visible to the eye generate signals through SAS which would provide aircraft damping. To engage the SAS, start the engine using normal operating procedure. After the engine is stabilized, turn the electrical control switch located on the control panel to power. The 3 no-go lights will illuminate and remain on for 15 to 60 seconds, at which time they will go out. The system may now be engaged by switching the axis switches to pitch, roll, and yaw. The system is now functional. In order to disengage the SAS, all 3 axis switches should be moved to off, or the emergency disengage button on the pilot or gunner cyclic grip may be pressed momentarily. Neither one of these steps turns off the electrical power, but simply disconnects the hydraulic power, causing the actuators to become mechanically locked. The entire SAS system, electrical and hydraulic, can be disengaged by turning the power control switch to off. If during the engaging procedure, one or more of the no-go lights fails to go off in the normal time, the built-in test equipment can be used to help find the trouble. The following procedure should be followed. Press the switch on the amplifier unit marked gyro test. Should the light go out, the gyro is faulty. If the light remains on, press the actuator test switch. If the light goes out, the actuator feedback circuitry is faulty. Should neither of these tests locate the trouble, the next step should be to replace the affected channel module. If this fails, a complete ground troubleshooting procedure should be begun. Stability, the dynamic requirement for an effective helicopter weapon system. The stability augmentation system ensures that the AH-1G is a stable weapons delivery platform. It provides rapid control response to wind and gusts and pilot compatibility, the desired features for the Army's newest combat aircraft.
Control of all aircraft, whether fixed or rotary wing, is accomplished through movement of control surfaces. The larger the aircraft, the larger those control effects must be, requiring stronger control systems to move them. This is particularly true in heavier rotary wing aircraft, where, in addition to the forces caused by aerodynamic effects related to lift, drag, thrust, and gravity, spinning rotor blades and associated rotor head components generate tremendous centrifugal forces. These forces tend to feed back into the flight control systems. In the H-21, full mechanical control can be maintained. The strength required to operate it mechanically would make it difficult to sustain flight of long duration. You can see how hard this man is working to move his cyclic control stick. Addition of collective pitch, difficult in itself, makes movement of the cyclic control stick even more difficult because of the added lift gravity forces to be overcome. To reduce the amount of physical effort required to operate these flight controls, heavier helicopters use hydraulic boost systems. Now watch the difference when the hydraulic boost is put into operation. Words are not necessary to explain the difference. You can see it. Notice how easily the blades are tilted. Nice and easy now, isn't it? Instead of using his own muscles, he's using the helicopter's hydraulic muscles. This is one of them, one of the 4 hydraulic servo actuators used in the H-21. It is similar to those used in all helicopters having hydraulic boost systems. Hydraulic fluid is pumped to those servo actuators under pressure. Movement of the cockpit control operates the pilot valve, which directs the fluid to either side of the actuator piston. The hydraulic pressure on the piston is transmitted through linkages to the upper flight controls. The power output of these servo actuators is considerable, as this simple demonstration will indicate. There is no trick to this. The strength of the man on the left has nothing to do with it. He's not pushing the big man. He's operating a valve that lets the hydraulic pressure do the pushing. Here's how the H-21 hydraulic flight control system works. It is similar to most hydraulic flight control systems. The major components are a reservoir, pump, pressure relief valve, accumulator, air pressure gauge, hydraulic line pressure gauge, shutoff or selector valve, line filter, servo actuators, return filter. The reservoir holds the necessary supply of hydraulic fluid. Next is the hydraulic pump, which supplies pressure for the system. It is rated at 1,000 pounds per square inch pressure at 1,650 RPM. Fluid is driven by the pump through the pressure relief valve, which limits the maximum pressure in the system to 1,150 pounds per square inch. The accumulator acts as a shock absorber for the system and maintains fluid under pressure for intermittent excessive demands of the system. Inside the accumulator, there is a floating piston which divides it into 2 chambers. One chamber is filled with air to a pressure of 300 pounds per square inch. When fluid under pressure from the hydraulic line forces the piston back against the air pressure becomes equal to hydraulic pressure in the line. In this case, the maximum, 1,150 pounds per square inch. Whenever the system calls for additional fluid under pressure, the accumulator makes it available, creating a corresponding drop in system pressure. In this case, 500 pounds per square inch. And when fluid flowing through the system is stopped, instead of pressure backing up into the system creating surge pressure, it is absorbed by the floating piston and air cushion in the accumulator. Fluid is directed through a micronic filter, which protects the valves, passages, and highly machined interiors of the servo actuators from damage due to contamination by foreign particles. The shutoff or selector valve is a modified 4-way valve, which in the off position connects the actuator pressure ports to the return line and prevents hydraulic lock so that the controls can be operated mechanically. Each of the 4 servo actuators has 2 ports, one for pressure fluid and one for return. As actuator pistons are moved one way or the other by fluid under pressure, fluid from the opposite side is forced into the return lines. Returning fluid passes through a hydraulic system filter, where it is cleaned again before replenishing the supply in the reservoir
and is available for further pumping through the system. A hydraulic line pressure gauge is located in the cockpit near the shutoff valve and reads in pounds per square inch. This gauge is connected to the hydraulic system anywhere between the shutoff valve and the servo actuator. In the H-19, there are 3 flight control hydraulic servo actuator units mounted on the main gearbox. Mechanical linkages from the cockpit controls actuate the pilot valves of the servo actuator and allow hydraulic fluid under pressure to enter the actuating cylinder and open a port to provide a return passage. In the event of hydraulic system failure, the mechanical linkage itself can operate the controls. One servo actuator controls the fore and aft movement of the star assembly. The other 2 servo actuators control lateral movement. All 3 servo actuators are operated by movement of the collective pitch linkage through a mixing unit, so that collective pitch can be varied without affecting cyclic pitch. The H-25 also uses 3 servo actuators. All are located under the floor. One located forward operates the lateral controls. The other 2 are located just aft of the cockpit. When facing forward, the one on the left is the longitudinal servo actuator. The one on the right, the one the repairman is removing, is the collective pitch servo actuator. An important thing to remember when removing a servo actuator is that although the ports are marked for pressure and return, the pressure and return lines are not. Therefore, both lines should be tagged to make sure of proper connections when a new servo actuator is installed. As you've already seen from looking at the trainer, the H-21 uses 4 servo actuators for hydraulic flight control boost. As you see them here, the one on the bottom is the longitudinal servo actuator. Above it is the collective pitch servo actuator. Next above it, and mounted crossways, is the lateral control servo actuator, and the top one is for directional control. Applicable tech orders contain troubleshooting charts to help the repairman in determining the causes of most common troubles. But some procedures are common to all hydraulic flight control systems. Be sure to remove all system pressure before disconnecting any hydraulic line or before filling a hydraulic reservoir. Whenever a new unit is installed or the lines have been opened up and reconnected, the system must be inspected. To do this on the H-25, the engine must be running or an auxiliary source of hydraulic pressure be connected in the system. Turn the shutoff valve to the on position and operate all of the flight controls so that hydraulic fluid will be pumped to all parts of the system. The collective pitch stick and cyclic pitch stick must be moved through the limits of all flight attitudes. Effective control of helicopter flight could be achieved without hydraulic boost, but the necessary increase in size and weight of bell cranks and quadrants to accomplish this would be undesirable. Hydraulic servo actuators are small, light in weight, highly dependable, and capable of power outputs well beyond the requirements of flight control systems. Hydraulic flight control systems are simple in design, and their operation is easy to understand. Generally, they consist of a reservoir, which contains the system fluid supply, a pump to supply system pressure, a pressure relief valve and regulator to maintain proper system pressures, and accumulator to absorb system shock or to aid operation in either overload or underload conditions, a selector valve to cut off pressure in the event of malfunction, one or more filters to protect the system from contamination. Yes, hydraulic flight control systems are simple in design and easy to understand. All of the components are rugged in construction, easy to maintain, and accessible for removal and replacement. It is most important that the helicopter repairman acquire a thorough knowledge of the operation of each and every component, so that the high degree of dependability designed into these hydraulic flight control systems is not lost through improper maintenance.